Welcome to this Fundamentals of Transport Processes 2. This is the second lecture in this course. In the first lecture, I had briefly reviewed the prerequisite for this course, that is the Fundamentals of Transport Processes 1, briefly what we did there and how. I hope you have had a chance to go back and look at those things, because we will be using similar material here as well. In this lecture, I would like to focus on what we will be doing in this course. Most of this course will be comprised of fluid mechanics, that is, how do you calculate the velocity field for fluid flow given the forces that are acting on that fluid. Okay, so now, in the last course, we had dealt primarily with transport of mass and energy. Transport of mass, I must emphasize, is confined to the case of very dilute solutions, where the solute concentration is small, so that the transport of solute does not affect the center of mass motion of the fluid as a whole. In this course, we will deal primarily with momentum transport, that is fluid mechanics, trying to predict the velocity field of the flow. Okay. The big difference between this and the previous course, as you would have anticipated, is that velocity is a vector. It has three components. This is in contrast to concentration and temperature fields for mass and heat transport respectively, which are both scalars. So, we could write out equation for just one quantity, okay. Whereas, in this case for the velocity field, it has three components. More importantly, those components depend upon the coordinate system that you are using to analyze the problem. If you analyze it in different coordinate systems, the components of the velocity will in general be different. Okay. So, that is something that has to be kept in mind. Since there are three components, one might think simplistically that I could just write down three equations for each of those components and solve them. However, these equations depend upon what coordinate system you are using to analyze the problem. In the previous Fundamentals of Transport Processes course, we had talked about the transport of heat and mass. These are given by the fluxes, the heat flux and the mass flux. These fluxes are vectors. Okay. They are in the direction of variation of concentration and direction of variation of temperature. Okay. So, in the case of scalar quantities such as heat and mass, the fluxes are in the form of vectors. You can anticipate that in the case of vector quantity such as the fluid velocity, the flux is going to be more complicated. Okay. And so, we will develop techniques in this course to analyze the velocity as a vector itself and the flux of the velocity as just one object, independent of the coordinate system that is being used to analyze the problem. And for that, we need to develop specialized skills. Okay. And I will come back to that. But first, what is the framework that we are going to be using? Okay. The framework is basically what is called the continuum approximation. Which I had discussed in the last Fundamentals of Transport Processes course as well. That is, we assume that the concentration, temperature and velocity are continuously varying functions of position. That is, they have one particular value at each and every location in space. Those values can also change in time. Okay. So, the idea is to identify these fields. Okay. The concentration, temperature and velocity fields as continuously varying functions in space and time, and see what constraints are imposed by conservation laws and constitutive relations on how these fields can vary. These constraints give us conservation equations, which are in the form of differential equations, telling you as you go from point to point in space and as you progress in time, how these fields vary. Okay. And if you can solve those differential equations, you can get by some kind of an integration procedure the entire velocity field, concentration field or temperature field. Now, once you have a continuously varying function, the advantage is that you can use all of the machinery that has been developed in calculus, okay, for differentiation and integration. But as in the case of the fundamentals of transport processes 1, it is a little more than that. Okay. And we will discuss what methods have to be developed for solving these field equations. Of course, the concept of field itself is an approximation. Okay. So, if I have a fluid say flowing past some object, I am defining velocity and temperature fields as continuously varying functions around this object. Okay. And what do I mean by the value of the temperature or the velocity at one particular point? Okay, the value at one particular position. So, if I have a coordinate system, okay, if I have some particular position x, y, z, okay, what is the meaning of saying the temperature at this point or the density at this point has some specific value? Okay. What that means is that I go to this particular location, sit on this location, okay, and construct a small volume around this location. Okay, construct a small volume around this location. Okay, so, this volume can be any shape. Okay. In this particular case, I will just take a cubical shape. Okay. So, this is the location, and at this particular location I construct a small volume of distance, let us say delta x, delta y, delta z, okay, and I count what is the total number of molecules of the fluid within this differential volume. Okay. And so, if I take the total number of molecules within this differential volume, my fluid density is defined as the summation over this entire volume of the mass of the molecule, okay, of each molecule over all the molecules within this volume, okay, divided by the volume itself. So, this is equal to the mass of the molecule times the number of molecules divided by the volume, that is the density. Note that in my definition I have delta V at the bottom. Okay. So, this is the mass per unit volume in the limit as the volume goes to 0, okay, in the volume as in the limit as delta x, delta y and delta z becomes smaller and smaller, this volume shrinks down to a point. At the same time, since the volume is decreasing, the number of molecules is also decreasing in such a way as in the limit delta x, delta y, delta z goes to 0, this limiting value has a unique limiting value, that is in the limit as delta x, delta y, delta z is going to 0, volume itself is shrinking, but however, the number of molecules there is also decreasing in such a way that the ratio of the two goes to a constant value as delta x, delta y, delta z are going to 0. So, that is the meaning of the density at one particular location. What about the velocity field? Okay. The velocity field, this as I said is a vector. Okay. This velocity field is a vector. Okay. So, for this vector I will use the notation u under bar, okay, to denote that it is a vector. Okay. So, here what I do is I go to this differential volume. Each molecule within this differential volume has one particular velocity or one particular momentum vector. Okay. So, I add up over all the molecules, okay, of the mass of each molecules times the velocity of each molecule. Okay. I add up the mass of each molecule times the velocity of each molecule, okay, and then I divide it by delta v. Okay. This is what is called the momentum density. Okay. This is what is called the momentum density. Okay. That is, this gives me the momentum per unit volume, okay, which is equal to the mass density times the mean velocity. Okay. So, if I have the mass density from here and I do this calculation and find out the momentum density, the velocity is just this whole thing divided by the mass density, okay, in the limit once again as the volume goes to 0. Okay. Limit. Okay, so, that is what is meant by saying the mean velocity at a particular point. So, that is the local pointwise value of the velocity at that particular location. Okay. Note that this is a vector velocity. Okay. So, if I for example, if I take the velocity of molecules in the x direction or in the y direction, some molecules will have positive velocity, some molecules will have negative velocity. You have to add all of those up. Okay. If the fluid is at rest, it does not mean the molecules are at rest. What it means is that the sum of the velocities of all molecules is equal to 0, not that their individual molecular velocities are equal to 0. Okay. So, this is a vector addition. It gives you a vector momentum density, and that divided by the density itself is the vector mean velocity of the fluid, okay, the fluid mean velocity. Now, of course, you cannot just take this volume going to 0, because as you make the volume smaller and smaller, there is going to come a stage at which there is either one particle in that volume or no particles in that volume. Okay. So, there is a limit to which you can take this delta v going to 0. Okay. This delta v that you are assuming has to be sufficiently small, that it is small compared to what are called the macroscopic scales in the flow. In this particular instant, that macroscopic scale will be the sphere diameter, for example. In the flow through a pipe, that macroscopic scale will be the pipe diameter. Okay. So, you have to make sure that the length scales of this differential volume are small compared to the macroscopic scales. However, they still have to be large compared to the microscopic scales. They have to be large compared to the molecular diameter for liquids, large compared to the mean free path, the time between collisions for gas molecules. Okay. So, as you make this differential volume smaller and smaller in such a way that the volume, the characteristic length is small compared to the macroscopic scales, but still large compared to the molecular sizes, you are going to come to a stage at which you can define the density and the mean velocity as quantities which are independent of the size of the volume, with the stipulation that it is large compared to microscopic scales, but still small compared large compared to molecular scales, but still small compared to microscopic scales. Okay. So, typically in the case of gases or liquids in fundamentals of transport processes 1, we had actually calculated the mean free path of a gas, okay, and that mean free path turns out to be of the order of 0.121 micrometers. Okay. So, that is pretty small. Any typical length scale that we encounter in process applications starting from millimeters to centimeters, meters is going to be sufficiently large that one can use the continuum approximation. Continuum approximation cannot be used when the sizes become sufficiently small that it is comparable to molecular scales, either the mean free path or the distance between or the molecular diameter. In that case, we have to actually do a complete molecular based simulation of the entire system. Okay. So, that is the only limitation of the continuum approximation. Okay. So, here I have defined for you the density, the mean velocity as fields, okay, and I have sort of tried to explain what those fields mean. Okay. The other distinguishing feature of this velocity field is that the velocity is a vector. Okay. As I said, at one particular location, the velocity field is a vector. It has a magnitude and a direction. Okay. And it can be resolved into three components. So, I can write, for example, if velocity u is equal to ux ex plus uy ey plus uz ez, can be written in terms of three components along the three different directions, where ex, ey and ez are the 3 unit vectors. The 3 unit vectors in the 3 directions. Okay. So, you can consider this as a combination of 3 scalars, okay, ux in the x direction, uy in the y direction, uz in the z direction. Okay. And that is one way to do it, to try to write conservation equations for each of these. However, there are properties of vectors which are independent of coordinate systems. Okay. So, for example, if I were to use a different coordinate system for this, okay, if I were to use a coordinate system consisting of x prime, y prime, z prime with 3 unit vectors in those 3 directions, then this will also be equal to ux prime times ex prime plus uy prime times ey prime plus uz prime times ez prime, and you get 3 other components. Of course, there should be equations for those as well, but the vector itself has an identity which is separate from the coordinate system that you are using to analyze it. For example, if I have a flow around a sphere in some particular direction, okay. So, in this particular case, let us say that this was a velocity field for the flow around a sphere, okay, in some particular direction. This vector is a physical quantity. Okay. That vector has an identity independent of the coordinate system, because it is actually gives you the direction of motion of the fluid at that particular location. Okay. So, vectors have identity which are independent of coordinate systems. So, rather than writing down equations for each particular scalar in this manner, I should be able to write down equations for the entire vector field itself, okay, and that will be one of the objectives of this course, to derive equations for the vector field itself, treating it as an object independent of coordinate systems. Okay. For example, there are certain things of vectors which are independent of coordinate systems. For example, the magnitude of a vector is independent of the coordinate system used. This also has to be equal to it is independent of the magnitude of the coordinate system used. Okay. Similarly, the dot product between 2 vectors, this is also independent of the coordinate system used, because that vector is actually a physical thing. Okay. So, this I can write it, expand it as ax bx plus ay by plus az bz. This is also equal to this is also equal to ax prime bx prime plus ay prime by prime plus az prime bz prime. It is independent of the coordinate system used. Okay. So, in this course, rather than work with the components of the vector, we will rather treat the vector as an object itself and try to derive conservation equations for the vector itself rather than for its components. Okay. So, that is an important difference between what we will be doing in this course and what we did previously. Okay. So, there are various vectors. velocity is a vector. Okay, it gives you the direction in which the fluid is moving at that particular location. Acceleration is a vector. Rate of change of velocity, that is a vector. Okay, it gives you the particular direction in which there is a change in velocity with respect to time. Okay. Force is a vector, momentum is a vector. There are other vectors that we defined in the previous fundamentals of transport processes 1. For example, the heat flux is a vector, gives you the direction in which heat is flowing. So, I can write the flux as Qx Ex plus Qy Ey plus Qz Z. This is a vector, gives you the direction in which heat is flowing. Similarly, mass flux is a vector. Okay. We also defined two other things as vectors in the previous fundamentals of transport processes 1 course. One of the important ones was the gradient. Okay. For example, the gradient of concentration, grad C. This is a vector. Okay. It is a vector, it is a derivative. Okay. So, it is a vector derivative. Okay. It gives you the rate at which concentration is varying as you travel in some direction at some location. Okay. So, this is the flux of the the Fick's law of mass diffusion tells you that the flux vector is equal to minus d times grad C. Flux heat vector is equal to minus alpha times K times the gradient of the temperature field. Okay. So, these are also vectors. Okay. Now, for a scalar quantity, its flux is a vector. For a scalar quantity, its flux is a vector. Okay. The concentration is defined at one particular location. The flux gives you the direction in which mass is traveling or mass is being transported at that particular location. Okay. So, the flux gives you the direction in which the concentration is being transported. Okay. So, for a scalar field, the vector is a flux. For a vector field, what is the flux going to be? Okay. So, let us discuss that a little bit. Okay. For a scalar field, for a concentration field, okay, the flux is being transported in one particular direction at a given location. Let me make one notational modification at this point. Okay. For our future discussion, it is going to be more convenient to label the axes as x1, x2, x3 instead of x, y and z. Okay. So, from now on we will use these axis labels. Okay. They will be more convenient for us when we deal with vector quantities. And at that same location, in that same coordinate system, the unit vectors will be defined as E1, E2 and E3. Okay. So, these are the unit vectors in the Cartesian coordinate system that I will use. Okay. And if I can derive conservation equation in this coordinate system for a vector, okay, without reference to its individual components, the conservation equation is a property of that vector itself. So, it is independent of coordinate system. It is going to be the same whether I use spherical or cylindrical coordinate systems, so long as my vector quantities and vector derivatives are correctly framed in that other coordinate system. So, we will talk about conservation equations for the quantity itself, not for the coordinate system. Okay. When it comes to actually solving a problem, of course, we have to refer to a coordinate system and we have to have a way of doing that, okay, doing the transforming these vectors and their derivatives from one coordinate system to another, and that we will do as we go through the course. So, we have a concentration field, okay, at one particular location. It is a continuously varying function. Okay. At that particular location, okay, so if C is the concentration, I can also define a flux vector at that particular location. A flux vector, that is the direction of transport of concentration. Okay. As I said, the flux vector is defined as J vector is equal to J1 E1 plus J2 E2 plus J3 E3, using a coordinate system where x1, x2, x3 are now the axis. These are the three components, okay. J1, J2 and J3 give you the fluxes in the three directions. Okay. So, I have J1 in this direction, J2 and J3, the three components of this flux. Okay. The resultant of these three gives me the direction in which mass is being transported. Okay. So, if I have a cross section perpendicular to this particular direction, I will get the maximum transport of mass across that. Okay. So, this gives me the direction in which mass is being transported. Okay. Now, let us do the same thing for not for a concentration field, but for a velocity field. Okay. So, in this particular case, what is getting transported is momentum. Momentum is a vector. Okay. So, at each particular point, I have one momentum vector. Okay. So, this momentum density vector will be rho times u, okay, with its three components. Okay. Rho u1, rho u2, rho u3. Okay. It has three components. Each of these components can be transported. Okay. So, the momentum in the x direction can be transported due to molecular diffusion. Momentum in the y direction can be transported due to molecular diffusion. Momentum in the z direction can also be transported due to molecular diffusion. For the momentum in the x direction, in the x1 direction, as I have defined it here. So, let us just go back and simplify and just consider the momentum in the x1 direction alone. This is the momentum in the x1 direction. This momentum in the x1 direction can be transported in any one of three directions. Okay. So, I can have x1 momentum being transported in the x1 direction, x1 momentum being transported in the x2 direction, and x1 momentum being transported in the x3 direction. Okay. So, there are three directions in which this particular component of the momentum, okay, rho u1, can be transported due to molecular diffusion. Similarly, for the second component, rho u2, this can also be transported in one of three directions. Similarly, the component in the third direction can also be transported in one of three directions. So, each component of the momentum can be transported in three directions, and there are three such components. Okay. So, the total comes out to 9 components of this particular flux for this vector momentum. Okay. This flux can also be defined as a single object. Okay. So, in this particular case for the mass flux, we had a single object, a vector, which defined the flux completely. It had one direction. That direction was the direction of transport of mass, because mass was a scalar. Okay. So, there was only one direction for the transport of mass. In the case of momentum, there are three components of the momentum, and each component can be transported in any one of three directions. Okay. So, therefore, you have an object which has 9 components. In the case of mass transport, there was only one direction, the direction of transport, because concentration was a scalar. In the case of momentum, you have two fundamental directions. One is the direction of the momentum itself, because momentum is a vector. The second is the direction of transport. Okay. That is, the direction of transport of momentum basically results in a force acting on some differential volume. Okay. So, let us make this a little more precise. Okay. If I have a particular location here, okay, and I have a surface. Okay. Imagine a surface at this particular location, okay, within the fluid. Okay. Okay. Because of the fluid flow past the surface, there is going to be a force exerted on the surface, this imaginary surface within the fluid. Okay. This force is due to the transport of momentum. Okay. Now, the force exerted is a vector itself. Okay. Force exerted is a vector, it has 3 components. Okay. However, the force itself is going to vary as I change the orientation of the surface. Okay. The force itself will vary as I change the orientation of the surface. Okay. So, if I have the orientation in one particular direction, I will get one particular force. If I change the orientation to some other direction, I will get some other force. Okay. And as I change the orientation in various directions, I will get different forces. Okay. The surface itself, the orientation of the surface can be defined in terms of the perpendicular to the surface. Okay. What is called the unit normal, that is, the unit normal to the surface, okay, gives me a direction. That unit normal is completely specifies the orientation of the surface. Okay. Now, if I have the unit normal, for example, in the x3 direction, okay, so this unit normal is actually E3, this is E3. Okay. Now, at the surface itself, there are forces acting in all 3 directions. Okay. As I said, because of the fluid flow, there could be forces acting perpendicular to the surface due to the pressure, for example. There could be forces acting along the surface due to shear, for example. So, forces could act in all 3 directions at this particular surface. Now, the stress is defined such that tau is called a second order tensor. Okay. Vector has only one fundamental direction, that is the direction of motion of the fluid in case of velocity, direction of transport in the case of concentration. This has 2 directions. Okay. It is written as the force per unit area, okay, at a surface with unit normal. Okay. So, in this particular case, J vector had 3 components. J1 was the flux in the x1 direction, J2 was the flux in the x2 direction, J3 was the flux in the x3 direction. Okay. This stress will now have 9 components. As I said, there are 3 components of momentum. Each component has 3 directions of transport. So, in general, I can write this as tau 11 E1 E1 plus tau 12 E1 E2 plus etcetera. It will have 9 components plus tau 33 E3 E3. Okay. So, it has a total of 9 components. Okay. What does each of these components mean? Okay. Tau 11 is equal to force per area in x1 direction acting at a surface with in x1 direction. Okay. So, let us spell it out in great detail. Okay. So, if I want to calculate the component tau 11 at one particular location, note that this is now a function of both of position and time. So, at one particular location, I go there, I construct a surface with unit normal in the x1 direction. Okay. So, this surface would have a unit normal in the x1 direction, and at the surface I measure the force acting on the surface in the x1 direction, divide by the area, and I get tau 11. Okay. Similarly, tau 12 is equal to force per area in x1 direction acting at surface with unit normal in x2 direction. Okay. So, in this particular case, if I want to measure what is tau 12, I go to this location once again, construct a surface with unit normal in the x1 direction, and then I measure what is the force acting here, okay, in the x2 direction, divide that by the area. Okay. So, this basically tau 11 gives me the flux of momentum in the x1 direction through a surface whose unit normal is in the x1 direction. Tau 12 gives me, so I am sorry, I should correct this. So, okay. So, I construct a surface whose unit normal is in the x2 direction. Okay. So, I construct a surface whose unit normal is in the x2 direction. Okay. So, the unit normal is the x1 x2 direction, and I measure the force in the x1 direction at this surface. Okay. I measure the force in the x1 direction at this surface, divide that by the area, and I get tau 12. Okay. So, a general formula, tau ij is equal to force per area in xi direction acting at a surface with unit normal in xj direction. Okay. And here I should add outward unit normal in the xj direction. So, these are what are called second order tensors. They have two fundamental directions associated with them. In the case of the stress, one is the direction of the force at the surface itself. However, the force does depend upon the orientation of the surface. So, the other direction is the direction of the orientation of the unit normal to that particular surface. Okay. So, one is the direction of transport, okay. The other is the direction of the momentum itself. So, momentum flux, there are two directions. One is the momentum direction, the direction in which force is exerted. The second is the direction of transport, that is the direction of the unit normal to the surface across which transport is occurring. So, these are second order tensors, and once again these will also come into our analysis. In this case as well, we will treat these as objects in themselves rather than worrying about their components. And this sort of makes it clear why I emphasize that we will be treating vectors themselves as objects, okay, because I told you that the velocity vector for which we are writing the conservation equation contains three components, and you would think in principle that I could write equations for each of those three. However, the flux in that equation now contains 9 components. So, I have to have constitutive relations for 9 of those components separately, okay, if I wanted to write equations in component form. Whereas, the way that we do it here, we will treat the velocity itself as a vector object, the flux itself as a tensor object, and derive relations between the flux, the velocity and the flux, write down conservation equation, constitutive relations for these. So, that is the major advancement that we will do in this course, and for that we have to develop the machinery of vector calculus. Okay. I will come back to more precise definitions of stress later on, but the reason I am bringing this up at this particular juncture is to just to emphasize why we are going to be going through all of the advanced vector calculus that we will be doing a little later. Okay. This is one fundamental second order tensor that we will be using throughout the course. Another fundamental second order tensor is the gradient of the velocity field. Okay. When I had talked about concentration fields, we had defined the concentration gradient as a vector. Okay. So, gradient of concentration, gradient of temperature, they are both vectors. They have three components. The component in each direction is the partial derivative of the concentration with respect to variation in that direction. So, partial c by partial x, if I go a small distance delta x in the x direction, keeping delta y and delta z a constant, the variation in delta c divided by delta x, while y and z are kept constant, as the partial derivative. So, this gives you a vector for a scalar field, the gradient. I could also take the gradient of a vector field, okay, and that would give me a second order tensor. The vector that we will use most often throughout this course is the velocity vector, because we are writing conservation equations for the velocity field. So, I can write the gradient of velocity as a second order tensor Okay, if I write it as gradient of the velocity vector, this becomes E1 E2 partial U2 by partial x1 plus E1 E3 partial U3 by partial x1 plus etc. plus E3 E3 partial U3 by partial x3. Okay, so this once again has 9 components. 3 components of velocity, they can vary in any one of 3 directions. Okay. This is a second order tensor. The gradient of velocity is a second order tensor. It is not the divergence, which is a scalar. It is not the curl, which is a vector. It is the gradient of the velocity, which is a second order tensor. Okay. Physically, what does this represent? What did the gradient of the concentration tell you? Okay. What did the gradient of the concentration tell you? Okay. You sit at one particular point. Okay. If I go a small distance, okay, delta x, okay, in some particular direction, the variation in concentration is equal to, okay, so if I have c and c plus delta c here, okay, if I go a small distance delta x in one particular direction, in this concentration field there is going to be a variation in the concentration. That variation in the concentration is equal to delta x 1 partial c by partial x 1 plus delta x 2 partial c by partial x 2 plus delta x 3 partial c by partial x 3, okay, which is equal to delta x 1 E 1 plus delta x 2 E 2 plus delta x 3 E 3 dotted with E 1 partial c by partial x 1 plus E 2 or I can write this as delta x dotted with gradient of c. Okay. So, the variation in concentration when you move a small distance from x to x plus delta x in some particular direction is the dot product of the distance traveled times the gradient of the concentration field. Okay. The same thing for the velocity field. Okay. Rather than dealing with a scalar, I am dealing now with a vector, but the principle is exactly the same. Okay. I have a velocity field, velocity vector, which is defined at each particular location in this field. Okay. At each position, there is a single valued velocity, single valued implying that the velocity at each particular location is uniquely specified. Okay. So, I have a velocity at one particular location u vector. I go a small distance delta x, okay, in one particular direction, and when I have traveled this distance at this new location, the velocity is equal to u plus delta u. Okay. The velocity has changed by an amount delta u. Delta u now is a vector. Okay. Delta u is the change in velocity. there is the new velocity minus the old velocity. So, operationally how you would calculate it is using the rules of vector addition. Okay. So, this is u and this vector, I superpose them at the same initial location. Okay. The vector difference now is this one, the resultant between the two. This vector difference is delta u. Okay. It has three components, delta u1, delta u2 and delta u3. Okay. It has three components, delta u is equal to delta u1 E1 plus delta u2 E2 plus delta u3 E3. Okay. Each of these can be defined in terms of the gradient of the velocity field. Okay. So, for example, the delta u1 I can expand it out and write it as delta u1 is equal to delta x1 partial u1 by partial x1 plus delta x2 partial u1 by partial x2 plus delta x3 partial u1 by partial x3. Okay. Or in analogy with the concentration field, this is just equal to delta x dotted with grad of u1, the component u1. Okay. Okay. Similarly, delta u2 is equal to delta x vector dotted with grad of u2, delta u3 is equal to delta x vector dotted with grad of u3. Add up all of these, delta u is equal to delta u1 E1 plus delta u2 E2 plus delta u3 E3. So, that means that delta u is equal to delta x dotted with grad of u1 E1 plus u2 E2 plus u3 E3, which is equal to delta x dotted with grad of u. Okay. Where this gradient of u now contains 9 components. Okay. This gradient of u, grad u, as I had defined it before, is equal to E1 E1 partial u1 by partial x1 plus E1 E2 partial u1 by partial u2 by partial x1 E1 E3 partial u3 by partial x1 plus etc. plus by partial x3. So, it now has 9 components. It has 2 indices, 2 directions. The first is the direction of the gradient. Okay. In all of these cases, the first one represents the direction of the gradient. Okay. The direction of with which you are taking the derivative. Okay. The direction with which you are taking the derivative. The second direction is the direction of the velocity vector itself. Okay. This velocity vector. So, these are fundamental tensors that we will be dealing with throughout this course. Okay. And so, I thought I would take this opportunity here to introduce them in order to give you their physical understanding. Okay. Now, once we have these tensors, we now have to write down conservation equations. As you can see, there is already one thing that has already appeared here is this gradient. Okay. This is a vector derivative. Okay. It contains 3 components, but it can be considered as an object in itself. It is a vector derivative. Okay. The gradient is one such, there is another one which is the divergence, and you already know there is a curl. Okay. So, that is a way of taking derivatives in 3-dimensional space, vector derivatives without reference to the underlying coordinate system. Okay. in terms of these vector derivatives, we can write down our conservation equations. We already did that in part 1, okay, where we wrote down, for example, for the concentration field, we wrote down an equation as partial C by partial T plus divergence of u c is equal to d del square C. These are all vector derivatives even though we actually calculated them in terms of their components. In this course, we will be calculating them as vector derivatives themselves without any reference to the underlying components. So, that is one part of it. The other part of it, okay, so once we calculate, once we use these vector calculus, we will be able to get equations for the velocity field that are similar to these. Okay. They call the Navier-Stokes equations, and I will just write them down here just to introduce them at this point. For an incompressible fluid, okay, or let us just take it for a gentle fluid. Okay, for a gentle fluid, these have the form by partial T plus divergence of rho u is equal to 0, and rho into partial u by partial T plus u dot grad u minus grad p plus mu divergence of you do not really have to try to understand these equations too much, except to realize that there is an equation for the density field. This first one is an equation for the density field. The second one is an equation for the momentum field, and these contain variables: the density rho, the velocity vector u vector, and there is also a pressure in this case P. Okay, so, they contain 3 variables. Okay. And they sort of look similar. See, the left hand side of the momentum equation here, okay, the left hand side of this momentum equation looks similar to this one. The right hand side looks similar to this one. Important difference: there is a pressure in the momentum equations which is not present in the concentration equations. In the fundamentals of transport processes 1, we actually derived the value of this pressure. We actually derived an equation for the pressure using shell balances for the flow through a pipe. Here we will do a more detailed derivation of the vector equations themselves. Okay. And once we derive these equations using the vector calculus that we will develop in the next few lectures, we then have to solve these equations. As usual, there is no simple way to solve these equations. Firstly, these equations are nonlinear. Okay. In this particular case, you have a term that goes as u dot del u. So, this is a nonlinear equation. Okay, so, there is no general solution, unlike the concentration equation where you do have a general solution. Okay. And the strategy that we will use is similar to what we used in the last fundamentals of transport processes 1. We derive equations in different limiting situations. The first limiting situation is diffusion dominated. Okay. As I said, the left hand side of this equation is basically the convection term, and so if your system is diffusion dominated, then the convection terms can be neglected and you can just solve the diffusion equation itself. We did that for the concentration field and the temperature field. We found out different ways of solving the diffusion equation using separation of variables, for example. Okay. Similarly, in the diffusion dominated regime, we will solve the equation for the velocity field without taking into account convection terms. The second is where convection dominated, okay, where we neglect the diffusion terms, but we cannot neglect the diffusion terms. As we saw in the case of the concentration equation, okay, when you neglect the diffusion terms, you neglect the highest order derivatives, and therefore, you cannot satisfy all boundary conditions. Even when convection is dominating, convection can only transport concentration along the flow, whereas for transport of mass momentum to a surface, at the surface itself there is no velocity perpendicular to the flow. So, you cannot have convection acting at the surface itself. Transport at the surface has to take place due to molecular diffusion. Okay. and even though convection is dominating, still as you go very close to the surface, the molecular diffusion mechanism has to kick in order for transport to take place, and therefore, diffusion will still be important over a small length whose thickness is determined in such a way that over this length scale there is a balance between convection and diffusion. Boundary layer theory that we had used in part 1. In this particular case, it is a little more complicated, because even if you neglect diffusion, you can still get non-trivial solutions because there is a pressure here. However, with just a pressure field, you cannot enforce tangential velocity boundary conditions at the surface. For that, you still need to postulate a boundary layer. The ratio of the convection and diffusion in this case is equivalent of the Peclet number, except that instead of mass or energy diffusion, you have momentum diffusion, kinematic viscosity, mu by rho or nu. Okay. When the Reynolds number is also, as you probably know, the ratio of inertia and viscosity. When the Reynolds number is small, okay, Reynolds number is small when the velocity is small, the characteristic length is small, or the kinematic viscosity is large for highly viscous fluids or for small length scale or velocity scales. You can neglect the convective terms in the diffusion in the Navier-Stokes equations and solve for the diffusion terms alone, the viscous terms alone. When the Reynolds number is large, okay, you can neglect the diffusion terms in most of the flow except very near boundaries, because if you neglect diffusion very near boundaries, you cannot enforce the tangential velocity boundary conditions, just as you could not enforce the concentration boundary conditions or the temperature boundary conditions at high Peclet number. In that case, it is necessary to postulate a boundary layer where viscosity is still important even though the Reynolds number is high, okay, because the Reynolds number based upon the boundary layer thickness is such that there is a balance between convection and diffusion. So, all of those techniques that we had developed for convection dominated and diffusion dominated transport in part 1 still apply, except that we now have to use it for vector fields. Okay. So, that is a broad summary of what we will be trying to do in this particular course. Okay. Methods are different. We will deal with vectors and tensors as objects in themselves, derive constitutive equations for those objects in themselves, okay. But the physical insight is much the same. There are situations where convection dominates, there are situations where diffusion dominates, and the interplay between convection and diffusion ultimately determines the rate at which the transport is going to take place. So, next class we will start developing the machinery of vector calculus that we will need in order for us to derive conservation equations and then solve them later on. So, with that I will end this lecture, and we will start our analysis of vector calculus in the next lecture. So, we will see you then.